This video is a pre-calculus video going over some example problems from 6.3. That's parametric equations in motion. Basically, I'm going to go over some application problems here that some students struggled with. Number 44 in your text, hitting a baseball. Kirby hits a ball when it's 4 feet above the ground with an initial velocity of 120 feet per second. The ball leaves the bat at a 30-degree angle with the horizontal and heads toward a 30-foot fence 350 feet from home plate. So, first of all, you need to set up your parametric equation. And what you're going to do is that x variable, or that x equation, it's always going to be in these types of problems the speed that you're hitting with times the cosine, it's always cosine for x, of the angle in which the ball leaves the bat or whatever the situation is. So the speed was 120 and the angle is 30 degrees, so x is 120 cosine 30 times t. Your y component is going to use your projectile motion equation. That's negative 16t squared plus your initial velocity times t plus your initial height. Well, if the ball was going straight up in the air, then we would use exactly that formula because sine of 90 degrees is 1, so we can use that exactly. For this, when the ball is leaving at an angle, you need to adjust that 120t to 120 sine 30 degrees t. So you'll always have negative 16t squared, and then you're going to add the speed times sine of the angle in which it's leaving times t plus your initial height. The initial height was 4 feet above ground, so that's what you use. You've got that set up. So the question is, will the baseball clear a fence, a 30-foot fence, 350 feet away? Well, so I want to know if I plug in 350 for x, I will know the time it takes, that's your t value, the time it takes to reach that fence, if it does reach it. So if I solve for t, in that simple equation, I get 3.37 seconds. Well, now if I plug that 3.37 seconds in for t in the y equation, I will know how high the ball is when it reaches the fence. So by plugging in 3.37 for t into my y equation, I get an answer of 24.59 feet. That represents the height of the ball after 3.37 seconds. Well, if the wall is 30 feet high, then that ball did not make it over the wall. And then the other part of the question was, can it be caught? No, you're not going to catch a ball that's 25 feet in the air. Now on your calculator, you would plug in this x equals equation. You would plug in this y equals equation when you're in parametric mode. Since your angle is in degrees, you need to be in degree mode. And then if you want a fence to show up at 350 feet away and have it be 30 feet tall, what you're going to need to do is you're going to set up another equation, x equals 350, that's how far away the fence is, and then y equals 30 times t divided by whatever you set your window t maximum at. Now, you could do x equals 350 and y equals 30. That would just put a dot at the top of the fence, and you'd be able to tell if it went over it or not from that. However, making the entire fence is a lot cooler. So if I look at my graph where I've put all this in, go to my y equals, I plugged all that information in. My window, I did my t min from 0 to 6. That you might just have to adjust. If you went from 0 to 3 seconds, well, the ball wouldn't quite reach the fence, and what you'd have is you'd have something that looks like this, and then it would stop before it gets back down to the ground, which just means you didn't go long enough. So You just have to adjust if that were the case. T-step, remember, if it's too small, it'll take forever to load. If it's too big, then it'll be kind of a jagged looking graph that won't look so nice. T minimum 0, that's where I'm starting. T maximum 400. I just wanted it to be bigger than 350 because I know that's where the wall is. And then your X scale, that depends on how you like the horizontal grid to look. Do you want a lot of tick marks or not? Your Y minimum 0 because that's ground level. And then your Y maximum would be 80. I just picked 80. Wouldn't have to be. You kind of have to play around with that also. You don't know probably for sure how high the ball is going to go. You know you got a 30-foot fence, so your number should be bigger than 30. Graph that, and you got a nice looking graph where the vertical distance on each point, that's how high the ball is. The horizontal distance, well, that's how far horizontally it has traveled. This vertical segment here, that's your fence. That's 30 feet tall. And it looks like it did not make it over the fence, which we already did or solved algebraically. Now, if I trace, I know the time that it took, so I can actually just type in 3.37 because it's the t value I can plug in. If I plug that in, I see I get just about the same answer I got algebraically, 24.49 instead of 0.59, which either way you see it did not clear the fence. I'll just briefly talk about number 45. It's basically the same setup, only what's different, I'll just read the problem. Suppose that the moment Kirby hits the ball in the last exercise, there's a 5 foot per second split second wind gust. Assume the wind acts in a horizontal direction out with the ball. And then it's the same question. Does the ball clear the fence? And if so, by how much does it clear the fence? If not, could it be caught? Well, the only thing you have to do differently, since the wind gust goes with the horizontal, is you need to add 5 to the horizontal. You add it right with the 120 cosine 30 degrees, add it in there, and then that whole answer is going to be multiplied by t. You don't adjust the y at all, and then you do this problem exactly as you did the last one. The next one I'll mention is number 46. Number 46 is going to be pretty similar, except for now you're throwing 2 balls towards each other. You got Linda in blue and Chris in red. Well, the big difference here is, since they're throwing the balls towards each other, you've got to be able to set this up so that they're not both being thrown from 0 kind of towards the right on your calculator. What you're going to need to do is, since Chris is on the right, we'll have him on the right throwing towards the left. For that to happen, since they are 78 feet apart, what you're going to do is you're going to have Chris's x component of his parametric equation start at 78. Whoops. You're going to have him start at 78 and then subtract the distance that the ball travels horizontally as time goes on. With that setup, the balls will be going towards each other on the calculator, and that's the main thing on this one, that I can see that you can set these 2 up so they're being thrown towards each other. To answer the problem's looking for when will the balls be closest together, or find the minimum distance between the balls. I'll say this, your hint algebraically would be to use your distance formula. Now this is going to mean plug your x sub 2 equation in, your x sub 1 equation in, your y sub 2 equation in, your y sub 1 equation in, and use your rectangular coordinate system. It's going to be a big long problem, but you've got all those equations set up. Just use x instead of t.